Tonight, we're going to talk about something you've never actually seen, even though you've been experiencing it every second of your life. The solar system is moving. Not just Earth spinning on its axis, and not just Earth orbiting the Sun. The entire solar system. The Sun, every planet, every moon, every comet, every grain of dust bound to our star is hurtling through the Milky Way at a speed you've never been told. The Sun isn't standing still. It never has been. And the path it takes through the galaxy is nothing like what most people think. By the end of tonight, you're going to understand how the solar system really moves through the galaxy and why it changes everything about how you see our place in it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Most people, if you ask them right now how the solar system moves through the galaxy, would describe a circle, the Sun orbiting the galactic center, planets trailing along, a neat, flat loop around the Milky Way. That picture is wrong. Wrong in a way that misses the most interesting part of the story entirely. The solar system's actual path through the galaxy is a corkscrew, a helix, a three-dimensional spiraling curve that simultaneously sweeps around the galactic center and bobs up and down through the galactic plane in a slow, enormous oscillation. Two motions at once, layered on top of each other, producing a path through space that looks nothing like anything you were shown in a classroom. And that shape is nothing like what most people picture. The Sun is moving through the galaxy at around 500,000 miles per hour, carrying every planet, every moon, every asteroid, every comet, every grain of dust, every molecule of every ocean and mountain and atmosphere and living thing along for the ride. You are moving at that speed right now. You have been every moment of your entire life. You will never feel it because everything around you, the ground, the air, the buildings, the sky is moving at essentially the same speed in the same direction. There is nothing nearby at rest to feel the motion against. But the motion is absolutely real. And to understand its shape, you need to understand what the Milky Way actually looks like from the inside. The Milky Way is a disk roughly 100,000 light-years in diameter, about 1,000 light-years thick, warped at the edges where it curls upward in one direction and downward in another. In the center sits a dense bulge of old stars surrounding a supermassive black hole, Sagittarius A. 4 million solar masses packed into a region smaller than the distance from Earth to the Sun. Spiral arms sweep outward from there, traced by young blue-white stars and glowing clouds of ionized hydrogen. And sitting about 26,000 light-years from the center, roughly halfway out, is the Sun. Not at the center, not at the edge. In the middle distance, inside a smaller structure called the Orion Arm, a modest address in an enormous city of stars. And from that address, the solar system orbits. The galactic orbit is the first motion, the fundamental motion, the one that gives everything else its context. The Sun takes approximately 225 million years to complete one full orbit around the galactic center. Astronomers call this a galactic year or a cosmic year. In the 4.5 billion years since the solar system formed from a collapsing cloud of gas and dust, the Sun has completed roughly 20 of these orbits, 20 laps around the entire galaxy. Now here is where the picture becomes more interesting than the basic orbital motion suggests. The Sun's orbital speed of around 500,000 miles per hour is not particularly extraordinary. Most stars in the Milky Way's disk orbit at broadly similar speeds. But the pattern of how orbital speed varies with distance from the galactic center is unexpected. In our own solar system, orbital speed drops dramatically with distance from the Sun. Mercury moves at about 107,000 miles per hour. Venus at about 78,000. Earth at about 67,000. Neptune, the outermost major planet, moves at about 12,000 miles per hour. The pattern is clear. Inner objects move much faster than outer objects. The reason is straightforward. The solar system's mass is overwhelmingly concentrated at the center in the Sun. Gravity drops off with distance, according to well-understood physics, and objects at greater distances need less speed to maintain a stable orbit. You would expect a galaxy to behave the same way. Most of the visible mass stars, gas, dust, appears to be concentrated toward the galactic center. Stars close to the center should orbit fast. Stars at the outer edge should orbit slowly. The velocity curve should drop off with distance, just like in the solar system. But when astronomers measured the actual orbital velocities of stars across the Milky Way, they found something deeply wrong with that expectation. Stars, far from the galactic center, were moving much faster than the visible mass could explain. The velocity curve, instead of declining as you moved outward, stayed essentially flat. Stars, at the outer edge of the disk, were moving at nearly the same speed as stars in the inner disk. This was impossible if the only gravitating mass was the mass astronomers could see. The implication was unavoidable. Something invisible was there, providing the extra gravitational pull. Something that didn't emit light, didn't absorb light, didn't interact with electromagnetic radiation in any known way, but something whose gravity was real and whose distribution extended far beyond the visible disk in every direction. Dark matter. The Milky Way's dark matter halo is thought to extend several 100,000 light-years from the galactic center, dwarfing the visible disk, which is only 100,000 light-years across. The dark matter halo is roughly spherical. It surrounds the disk in all directions, and it outweighs the visible matter, all the stars, all the gas, all the dust, by a factor of roughly 5 or 6. Most of the Milky Way, by mass, is invisible. The Sun is orbiting not just through a galaxy of stars and luminous gas, but through a vast, invisible gravitational scaffolding whose fundamental nature remains unknown despite decades of searching. Physicists have built increasingly sensitive detectors buried deep underground in mines, shielded from every known source of background radiation, and waited for years for a single confirmed interaction with a dark matter particle. As of today, nothing definitive has arrived. Dark matter remains detectable only by its gravity, never directly, and yet it is almost certainly there. The rotation curve of the galaxy demands it. The velocities of galaxy clusters demand it. The large-scale structure of the universe demands it, and the solar system moves through it, constantly embedded in it, shaped by it, orbiting within it the way a fish is embedded in water. Dark matter particles, whatever they are passing through you right now, through your body, through the floor, through the planet. You will never feel them. They pass through ordinary matter the way light passes through glass. But they are there. They are everywhere, and their gravity is quietly shaping every orbit in this galaxy, including ours. Now comes the second motion, the one almost nobody discusses. The one that transforms the orbit from a flat circle into a corkscrew. The galactic disk is not empty. It contains stars, gas clouds, dust, molecular clouds, billions of solar masses of material distributed throughout its thickness. And all of that distributed mass has gravity. Not gravity pulling toward the galactic center. Gravity pulling toward the galactic midplane. When an object is above the midplane, the mass of the disk below it pulls it downward, back toward the plane. When it overshoots and goes below, the mass above pulls it back upward. The result is an oscillation, a pendulum-like motion perpendicular to the galactic plane. Every star in the disk is doing this, rising above the midplane, being pulled back, falling through, overshooting to the other side, being pulled back again, rising back up. A slow, continuous bobbing motion superimposed on the orbital motion around the galactic center. The Sun is no exception. As the Sun sweeps around the galactic center in its 225 million-year orbit, it simultaneously moves perpendicular to the galactic plane in this oscillation. The period of the oscillation, the time to complete one full up-down-up cycle, is estimated at somewhere between 60 and 90 million years. That's considerably shorter than the orbital period. So, in a single galactic orbit, the Sun bobs through the galactic plane roughly 2 to 4 times. Up through the disk, all the way above it, back down through the plane, below the disk, back up again, over and over, while simultaneously sweeping around the galactic center. The combination of these two motions, the orbital sweep and the perpendicular oscillation, produces a three-dimensional path through the galaxy that looks nothing like a flat circle. It looks like a helix, a corkscrew. If you could somehow freeze the galaxy in place and trace the path the solar system has taken over its lifetime, you would see not a flat ring, but something like an enormous spring, coiled and then bent into a ring, 20 coils around for 20 galactic orbits, with each coil representing the up-down oscillation. That is the actual shape of our journey. That is how the solar system really moves through the galaxy. And at this moment, the Sun is about 80 light-years above the galactic midplane, near the top of one of its oscillations, heading back toward the plane in the coming tens of millions of years. There is a third component to the motion, subtler than the first two, rarely mentioned outside of technical literature, but real. The Sun has its own individual velocity relative to the average motion of the stars in its local neighborhood. Astronomers have a specific term for this. They define something called the local standard of rest, a reference frame representing the mean velocity of nearby stars, averaging out the random individual motions to find the bulk orbital motion of the local stellar neighborhood. The Sun doesn't perfectly match that average. It has a small additional velocity relative to it. The direction of that extra drift is toward a point in the sky in the constellation Hercules. Astronomers call that point the solar apex. The speed of the drift is modest, roughly 12 miles per second, relative to the local standard. Set against around 500,000 miles per hour of orbital speed, 12 miles per second is small. But it is not zero. And over millions of years, it adds up. It means the Sun is gradually changing position relative to its nearest stellar neighbors. Stars that are currently close to the solar system will slowly drift farther away. Stars currently farther away will slowly approach. Over the next 10,000 years, the closest star to Earth will no longer be Proxima Centauri. Proxima is currently moving toward us, getting slightly closer with each passing millennium. it will reach its minimum approach distance of roughly 3.1 light-years in about 27,000 years. Then begin pulling away again, as its orbital path carries it in a different direction from ours. Eventually, some other star, currently more distant, will drift to become our new nearest neighbor. Nothing in the galaxy is fixed. Every star is a traveler on its own individual path. Those paths occasionally bring stars near each other, like passing ships before carrying them apart again. The neighborhood is not stable. It is not permanent. It is a temporary arrangement of travelers who happen to be moving in broadly similar directions at this particular moment in galactic history. Now consider what all of this motion means for Earth's history. Because this is where the motion stops being abstract and becomes consequential. The solar system is not sitting still in a quiet, stable corner of the galaxy, immune to changes in its surroundings. It is moving continuously through an environment that changes as the orbit progresses. And those changing environments have almost certainly shaped the history of life on this planet in ways that are only beginning to be understood. The galactic disk is not uniform. It has regions of higher star density and regions of lower density. It has the spiral arms traced by young, hot, massive stars and dense concentrations of gas where stellar nurseries blaze and supernova explosions are far more frequent than in the quieter interarm regions. And it has the gaps between the arms, stretches of lower density where conditions are calmer and the rate of intense stellar activity is reduced. As the Sun orbits the galaxy, it passes through these different regions. But the way it does so is more interesting than a simple in and out story. The spiral arms are not solid walls. They are not permanent structures that stars smash through. They are density waves, patterns in the rotating disk where matter temporarily bunches together before moving on. The analogy that works well is a traffic jam on a highway. The jam has a location. It appears to sit at a particular place on the road, but the individual cars are always moving through it. Cars, slow as they enter the jam, creep through it, then accelerate out the other side. The jam stays while the cars move. The jam is the wave, not the cars. Spiral arms work the same way. Stars and gas clouds orbit the galaxy at their own speeds. The spiral arm pattern rotates around the galaxy at its own speed. Those two speeds are generally different, so stars move into an arm, spend time inside it, and then move out the other side. The arm persists as a rotating density wave while the individual stars flow through it. Here is the crucial detail for the solar system. The Sun's orbital speed is close to the speed at which the spiral arm pattern itself rotates. This is called the corrotation resonance, and the Sun is thought to be near the corrotation radius of the Milky Way. The consequence is that the Sun doesn't repeatedly plunge deep into the major spiral arms the way most other stars in the disk do. Stars with orbital speeds significantly different from the arm pattern's rotation speed get swept into and out of arms repeatedly as the pattern laps them or falls behind them. The Sun, being near corrotation, hovers near the edge of the arm structure instead. It spends relatively little time deep inside the densest, most active regions of the major arms. This may matter a great deal. Spiral arms are the most active environments in the disk. Massive stars form there in extraordinary numbers. Those massive stars live fast, burning through their nuclear fuel in just a few million years and end in supernova explosions. A supernova, within a few hundred light-years of the solar system, could be consequential. The intense burst of radiation, X-rays, and gamma rays could damage the ozone layer, increasing the ultraviolet radiation reaching Earth's surface. The expanding shock wave of the explosion could compress nearby gas clouds and trigger new star formation, but could also disturb the outer solar system. And supernovae are the primary source of cosmic rays. High-energy particles accelerated to near light speed in the explosion's shockwave that reached the inner solar system. A solar system moving through a region dense with recent supernovae would experience a higher cosmic ray flux. More energetic particles reaching Earth. More ionization in the atmosphere. More potential disruption to the biology of the surface. Some researchers have proposed that the Sun's position near the corrotation radius and the resulting relatively calm galactic environment it has inhabited for much of its history may have contributed to the long-term stability that allowed complex life to develop and persist on Earth. The idea is that there is a galactic habitable zone, not just a range of distances from the galactic center, but a region of the galaxy where the environment is neither too active nor too sparse, where the right elements are available, but catastrophic radiation events are not too frequent. The Sun may sit within that zone. Whether this is a coincidence or something more meaningful is genuinely unknown. But the mechanism is physically real. The galactic environment changes as the solar system moves through it, and the history of life on Earth was written in a particular galactic environment, not in some abstract isolation from the rest of the Milky Way. There is evidence, written in Earth's rocks, that the galaxy has touched us directly. In the last few years, analyses of deep-sea ferromanganese crusts, mineral deposits that build up slowly on the ocean floor over millions of years, have revealed elevated concentrations of radioactive iron-60 at layers corresponding to roughly 2.6 million years ago, and perhaps another layer around 8 million years ago. Radioactive iron-60 is not produced in significant quantities by ordinary stellar processes. It is, however, a product of supernova explosions. And the only way to get supernova-produced iron-60 into Earth's ocean sediments is for a supernova to have gone off close enough to the solar system that the expanding debris cloud reached us. The half-life of iron-60 is about 2.5 million years. The fact that we can still detect it in layers corresponding to 2.5 million years ago means the supernova happened close enough and recently enough to leave a measurable trace. The estimates suggest a supernova within perhaps a few hundred light-years of the solar system, possibly part of a cluster of massive stars that formed nearby. Life on Earth at that time continued. The supernova didn't sterilize the planet, but it was there. The galactic environment reached into the inner solar system and left a chemical signature in the rocks. The galaxy and the history of Earth are not separate stories. They are the same story, told at different scales. The vertical oscillation through the galactic disk adds its own layer of consequence. When the solar system passes through the denser midplane of the disk, it encounters more gas, more dust, more molecular clouds. And far beyond the planets, the solar system is surrounded by the Oort cloud. The Oort cloud is perhaps the least known major structure of the solar system, despite being enormous. It is a vast, loosely organized reservoir of icy bodies, the primordial remnants of the solar system's formation, extending from roughly 2,000 astronomical units from the Sun out to perhaps 100,000 astronomical units. 1 astronomical unit, the Earth-Sun distance, is about 93 million miles. The outer Oort cloud extends to perhaps 9 trillion miles from the Sun. It contains an estimated several hundred billion to several trillion icy objects, most of them small, all of them moving in slow, wide orbits in the cold dark at the edge of the solar system's gravitational influence. These objects are bound to the Sun by gravity, but barely. The gravitational hold is so weak that even modest perturbations from outside can alter their orbits significantly. And what perturbs them? Passing stars, massive gas clouds, and the gravitational tide of the galactic disk itself. The gravitational tide. This is not a metaphor. As the solar system orbits the galaxy and oscillates through the disk, the distribution of mass around it changes. When the solar system is well above the midplane, the disk's mass is mostly below. When it passes through the midplane, mass is more evenly distributed above and below. These changes in the distribution of nearby mass create changing gravitational stresses on the Oort cloud. The Oort cloud objects, loosely held, respond to those stresses. Some objects get nudged from stable, distant orbits into new paths that carry them inward. Long, elliptical orbits that bring them through the inner solar system. These are long-period comets, the ones that arrive on highly elongated orbits, swinging around the Sun once in thousands or tens of thousands of years before heading back out. Many long-period comets are thought to have been stored in the Oort cloud for billions of years before something disturbed them and sent them inward. That something includes the galactic tide. Some researchers have examined whether there is a pattern to the timing of comet showers and large impact events on Earth, whether the solar system's oscillation through the galactic plane leaves a signature in the geological record in the form of periodic spikes in impact rates. The analysis is difficult. The geological record is incomplete, and identifying true periodicity in events separated by tens of millions of years requires careful statistical methods. The evidence for a clear, regular periodicity is debated. But the underlying mechanism, the galaxy reshaping the comet reservoir as the solar system oscillates, is real physics. The galactic tide is an accepted phenomenon. The Oort cloud's sensitivity to perturbations is well established. The connection between galactic position and comet flux is not hypothetical. Whether it leaves a detectable signature in Earth's history is the unresolved question. What is not unresolved is that the galaxy is an active environment the solar system is moving through, not a static backdrop. An environment with structure and dynamics that reaches, however gently, into the solar system itself. To understand where the solar system actually is within the Milky Way, and what that position means for its journey, requires knowing something about the spiral arm structure of the galaxy. The Milky Way has 4 major spiral arms. The Perseus arm curves through the outer galaxy. The Sagittarius Carina arm lies closer to the galactic center than the Sun. The Scutum Centaurus arm curves inward toward the galactic bar. The Norma arm traces through the inner disk. The Sun sits between the Sagittarius Carina arm and the Perseus arm, inside a smaller structure, the Orion arm, that was long thought to be merely a minor spur connecting the 2 major arms. Recent observations have revised this view. Radio surveys of star-forming regions and the Gaia data on stellar positions have shown that the Orion arm is longer and more substantial than previously thought. It may extend for 25,000 light-years or more. The distinction between a major arm and a minor spur is not entirely sharp, and the Orion arm may be closer to a genuine arm than the traditional picture suggested. What this means for the solar system's position is that we sit not in the backwater of a minor connector between real arms, but in a substantial arm structure of our own. The view of the galaxy from our location looking out in different directions gives us perspectives along the arm, across to the Perseus arm on one side, and across to the Sagittarius Carina arm on the other. Most of the bright, well-known stars in our night sky lie within a few thousand light years. They're local. The galaxy extends 100,000 light years across, and our naked eye view samples only the tiniest sliver of it. The vast majority of the galaxy is invisible to the unaided eye, not because it's too far, but because its light is blocked by dust in the galactic plane. The Great Rift, visible in the Milky Way, on a dark night, that dark lane splitting the band of light, is not empty space. It's dust. Interstellar dust grains, each smaller than a particle of smoke, absorbing and scattering the light of stars behind them. The center of the galaxy, 26,000 light-years away, is completely invisible to ordinary optical telescopes. All that dust blocks the view. It was only when radio telescopes and infrared instruments were developed in the mid-20th century that astronomers could finally see through it and observe the galactic center directly. What they found there has been consistently surprising. A dense cluster of young, massive stars circling the central black hole. Gas clouds moving at hundreds of miles per second. X-ray filaments and infrared sources dense beyond counting. And, at the very center, Sagittarius A, 4 million solar masses in a region smaller than the solar system's silent now, barely whispering compared to the active galactic nuclei seen in other galaxies, but capable of periodic outbursts that brighten the galactic center dramatically. Astronomers have found evidence that Sagittarius A was far more active a few million years ago. Structures called Fermi bubbles, enormous lobes of gamma-ray emission extending tens of thousands of light-years above and below the galactic plane, appear to be the remnants of a massive outburst of energy from the galactic center in the geologically recent past. The bubbles were discovered by NASA's Fermi Space Telescope in 2010. They extend about 25,000 light-years above and below the galactic plane. The energy in them is extraordinary. Whatever happened, a major accretion event onto the black hole, or an enormous burst of star formation in the inner galaxy. It was violent enough to blow hot gas far out of the disk and leave a structure visible across most of the sky. The solar system was already near its current galactic position when that event occurred. The remnants of that outburst are visible today if you look at the right wavelengths. The galactic center is not as quiet a place as it appears from 26,000 light-years away. In 2013, the European Space Agency launched the Gaia spacecraft to a gravitational equilibrium point about 930,000 miles from Earth. Its mission: measure the positions, distances, and velocities of more than 1 billion stars with precision that had never been achieved before. The angular precision of Gaia's measurements is almost incomprehensible. It can measure the apparent position of a star to within a few tens of micro-arcseconds. A micro-arcsecond is 1/1,000,000th of an arcsecond. An arcsecond is 1/3600th of a degree. To visualize the precision, it is equivalent to measuring the apparent diameter of a human hair at a distance of about 1,000 miles. From that precision, Gaia derives distances and velocities. And with velocities of 1 billion stars, the dynamics of the Milky Way become visible at a level of detail never previously possible. The Gaia data has revealed that the Milky Way is more complex and more disturbed than the classic model suggested. The disk has large-scale oscillations, not just the warped edges known for decades, but internal ripples, corrugations, in which stars at different galactic radii are at systematically different heights, above or below the midplane, moving in different vertical directions, like a slow wave passing through a sheet of water. The velocities of disk stars are not smoothly organized. There are coherent structures in velocity space, groups of stars moving together in ways that don't fit a simple rotating disk model. Some of these structures are understood as the result of resonances with the spiral arms or with the galactic bar-stable orbital configurations that stars can settle into and remain in for long periods. Others are more puzzling and are still being analyzed. The most striking disturbance visible in the Gaia data is attributed to the Sagittarius Dwarf galaxy. The Sagittarius Dwarf is a small satellite galaxy containing a few tens of millions of stars that has been orbiting the Milky Way for billions of years. It is on a highly inclined orbit that repeatedly brings it through the plane of the Milky Way's disk. Each passage is not gentle. The Sagittarius Dwarf has already lost most of its mass to tidal stripping by the Milky Way. Its stars have been scattered into long streams, the Sagittarius stream that wrap around the Milky Way several times. The last few passages of the Sagittarius Dwarf through the disk sent gravitational shock waves through the galactic plane. Those shock waves are the corrugations and velocity disturbances seen in the Gaia data. We are still inside those ripples. The disk is still ringing from those passages. The solar system is moving through a galaxy that has been disturbed repeatedly by gravitational encounters with satellite galaxies, and the evidence of those disturbances is written in the velocities of the stars around us. The Milky Way is not a peaceful, smooth structure rotating in gentle equilibrium. It is a dynamic system, gravitationally complex, historically disrupted, still reverberating from events that happened hundreds of millions to billions of years ago. The understanding of the solar system's true motion through the galaxy was built slowly, over centuries of observation, by people working with instruments and mathematics that improved with every generation. For most of human history, the Milky Way was a mystery. The ancient Greeks debated what it was. Aristotle, the most systematic thinker of the ancient world, concluded it was an atmospheric phenomenon, something in the upper air above Earth, not something in the sky proper. He was wrong, but his reasoning was not unreasonable, given the absence of telescopes. The change came in 1610, when Galileo turned one of the first telescopes toward the Milky Way and resolved its faint glow into individual stars. Innumerable stars, too numerous to count. He couldn't know the scale. He couldn't know we were inside it. But he knew it was stars, not air. Understanding that the sun was part of a disk of stars, and that this disk had a center and a structure, took much longer. William Herschel, one of the greatest observational astronomers of the 18th century, tried to map the galaxy in the 1700s by counting stars in different directions. His logic was correct. If we're inside a disk, there should be more stars in directions along the disk than perpendicular to it. He counted them painstakingly, telescoping across the entire sky. And he found the asymmetry he expected. But he made a fatal assumption. He assumed he could see all the way to the edge of the disk, in every direction. He couldn't. Interstellar dust, which he had no way of knowing about, was absorbing and scattering the light of distant stars, making them invisible. The stars seemed to thin out in distant directions, not because the disk ended there, but because the dust was hiding them. His map showed the Sun near the center of a relatively modest disk. Both conclusions were wrong. The Sun is far from the center, and the disk is far larger than Herschel's map suggested. The dust hid the truth. It would keep hiding it for another century. The breakthrough came in the early 20th century from an unexpected direction. Harlow Shapley, an American astronomer working at the Mount Wilson Observatory in California, was studying globular clusters, spherical swarms of hundreds of thousands of ancient stars that orbit the Milky Way from the halo regions above and below the disk. Shapley recognized something important. Globular clusters should be distributed roughly spherically around the galactic center. So the center of the distribution of globular clusters should mark, approximately, the galactic center. He measured distances to dozens of clusters, using a type of variable star called a Cepheid as a distance indicator, and plotted their positions across the sky. The result was unmistakable. The clusters were not distributed symmetrically around us. They were concentrated strongly toward the constellation Sagittarius. The galactic center was in that direction, and it was very far away. The Sun was not at the center of the galaxy. It was far out in the disk. This was one of the most significant discoveries in the history of astronomy, and it arrived wrapped in a genuine sense of humiliation. Copernicus had removed Earth from the center of the solar system in the 1500s. Now, Shapley was removing the Sun from the center of the galaxy. Every time humanity had assumed it occupied a special position at the center of something, it turned out not to. The pattern was consistent and sobering. In the decades following Shapley's work, astronomers Jan Oort and Bertil Lindblad worked out the dynamics of the galactic disk by studying the velocities of nearby stars. They found that stars closer to the galactic center moved faster. Stars farther out moved somewhat slower, but both groups were moving in the same general direction. The disk was rotating differentially. From those velocity patterns, they inferred the Sun's orbital speed and its distance from the galactic center, obtaining values remarkably close to modern measurements, despite their much more limited instruments and data. In the 1940s and 1950s, radio telescopes opened a new window on the galaxy. Hydrogen, the most abundant element in the universe, emits radio waves at a wavelength of 21 centimeters when the electron in a hydrogen atom undergoes a specific transition. This 21-centimeter radiation passes through the interstellar dust that blocked Herschel's optical view. With radio telescopes, astronomers could finally map hydrogen gas across the entire galactic disk. The spiral arms became visible as concentrations of gas. The overall scale and structure of the Milky Way became measurable in ways that optical astronomy had never allowed. The picture that emerged was of a large barred spiral galaxy, a structure with a long bar of stars through its center and spiral arms emerging from the ends of the bar. And then came Vera Rubin. In the late 1970s, Rubin and her collaborators measured the rotation curves of spiral galaxies in detail never previously achieved. They found that the outer regions of galaxies were rotating faster than the visible mass could explain. The rotation curves were flat when physics said they should decline. Fritz Zwicky had pointed to similar anomalies in galaxy clusters in the 1930s and proposed unseen mass, what he called dunkel materia, or dark matter. But the astronomical community had largely not taken it seriously. Rubin's systematic observations of dozens of galaxies made it impossible to ignore. The dark matter was real. Its gravitational effects were undeniable. And when astronomers turned the same analysis on the Milky Way, the result was the same. The solar system is orbiting not just through a galaxy of stars and gas, but through an enormous, invisible dark matter halo, whose mass exceeds all the visible matter combined. We have been moving through it for 4.5 billion years. We will continue moving through it for billions more. We still don't know what it is. There is a feature of the Milky Way that wasn't appreciated until the latter half of the 20th century, the bar. The Milky Way is not a classic, unbarred spiral galaxy. It is a barred spiral, with a long, dense bar of stars cutting through the central bulge. The bar extends roughly 27,000 light-years across, oriented at an angle to our line of sight. Its exact angle, how much it's tilted relative to our direction, is still debated. But infrared surveys from the COBE satellite in the 1990s and subsequent observations established its existence beyond doubt. The bar rotates, but it rotates differently from the disk. Where the disk rotates differentially, inner stars faster, outer stars slower, the bar rotates as a rigid body, with all its stars moving at the same angular speed, like a solid wheel. The speed at which the bar rotates is called the bar's pattern speed, and it creates resonances in the disk, where the orbital frequencies of stars match the rotation rate of the bar in various ratios. At those resonance locations, the gravitational interaction between the bar and disk stars is repeated and coherent, and it can pump energy into the orbits of disk stars, changing their paths significantly over time. The Sun sits in the disk, far from the galactic center, but the bar's resonances extend throughout the disk, and some analyses suggest the Sun may be near one of these resonance locations. If so, the bar's rotation has been subtly influencing the Sun's orbit for billions of years. The Milky Way's internal structure shapes the solar system's orbit in ways that go beyond simple circular motion in a disk. The bar, the spiral arms, the dark matter halo, the disk's vertical gravity, all of them contribute to the actual path the solar system follows through space. The orbit is not simple. It was never simple. Now, step all the way back, pull the perspective out until the Milky Way itself is small. Because the Milky Way is also moving. The entire galaxy is being pulled through intergalactic space by a vast concentration of mass. The Great Attractor. This is not a metaphorical name for something vague. The Great Attractor is a real, specific concentration of matter located roughly 250 million light-years away in the direction of the Centaurus and Norma constellations. It is a region where the universe is denser than average, packed with galaxy clusters and superclusters, and its collective gravity is pulling hundreds of nearby galaxies toward it, including the Milky Way, including Andromeda, including the entire local group. The Milky Way is falling toward the Great Attractor at roughly 1.4 million miles per hour. That's on top of the galaxy's own internal orbital motions. And the Great Attractor itself is being pulled toward a structure called the Shapley Supercluster, located more than 500 million light-years away. The Shapley Supercluster is one of the most massive structures in the known universe. It contains the equivalent of tens of millions of times the mass of the Milky Way, distributed across a vast region of the universe. Its gravity reaches across hundreds of millions of light-years and pulls our local region of the universe toward it. There are layers upon layers of motion, each one nested inside the next. Earth orbits the Sun. The Sun orbits the galactic center while oscillating through the galactic disk. The Milky Way falls toward the Great Attractor. the great attractor falls toward Shapley. And at the largest scales, the universe itself expands, stretching the space between galaxy clusters, carrying them apart from each other while gravity binds them internally. Motion is not the exception in the universe. Motion is the default. Motion is the rule. Stillness is the illusion. The Andromeda Galaxy is coming. Let that settle for a moment. Andromeda, catalogued as Messier 31, is the largest galaxy in the local group, containing roughly 1 trillion stars, compared to the Milky Way's estimated 200 to 400 billion. It sits about 2.5 million light-years away. In the night sky, on a clear, dark night far from city lights, it's visible as a faint smear of light in the constellation Andromeda, the most distant object visible to the unaided human eye. And it is on a collision course with the Milky Way. This is not speculation or a theoretical possibility. It is established by measurement. The Hubble Space Telescope spent years carefully tracking the position of Andromeda against background galaxies much farther away, measuring the galaxy's tiny transverse motion across the sky. Combined with earlier spectroscopic measurements of its radial velocity, how fast it's approaching along our line of sight, the full three-dimensional velocity of Andromeda has been worked out. Andromeda is approaching at roughly 68 miles per second. The collision will begin in about 4 to 5 billion years. The word collision overstates what will happen to individual stars. Galaxies are almost entirely empty space. The distances between stars are so enormous that when two galaxies merge, the probability of any two stars actually crashing into each other is negligibly small. What happens instead is gravitational chaos at enormous scale. As Andromeda approaches, its gravity will begin distorting the outer regions of the Milky Way long before the disks overlap. Long streamers of stars will be pulled out of both galaxies. The gas clouds in both galaxies will collide with each other. Gas does interact directly, unlike stars, and those collisions will compress the gas and trigger massive bursts of star formation. Thousands of new stars will ignite in the compressed regions. Many will be massive, burning hot and fast, and will end in supernova explosions within a few million years. The two galaxies will pass through each other, swing apart, then fall back together. The merger will take hundreds of millions of years to complete. Multiple passes before the two systems finally settle into a single object. The end result will not be a spiral galaxy. It will be an elliptical galaxy, stars moving in random orbits in all directions, rather than the organized rotating disk we inhabit now. Astronomers sometimes call this future object Milkomeda. Its appearance will bear no resemblance to either the Milky Way or Andromeda as they look today. What happens to the Sun and its planets during the merger? Computer simulations run repeatedly with slightly different starting conditions to capture the range of possible outcomes. The most common outcome is that the solar system gets thrown into a larger, more eccentric orbit in the resulting merged galaxy. The gravitational chaos of the merger scrambles orbital patterns, throwing some stars into tighter orbits nearer the central mass, and others into wide, looping orbits in the outer regions. The Sun will not be gone. Its planets will almost certainly remain bound to it. The solar system will survive the merger as an intact unit. But where in the resulting galaxy it ends up is genuinely uncertain. Some simulations place it in the outer regions of the merged system. Others keep it closer to what was once the galactic center. the night sky will look unrecognizable. If anything is alive on Earth 4.5 billion years from now, which the sun's own evolution makes somewhat doubtful, it will look up at a sky blazing with the light of a galaxy in the middle of a merger. A sky no human has ever imagined. Here is what this all means, taken seriously. Human experience is calibrated to the scale of a human life. The things your body can perceive. The distances you can walk or drive or fly. The timescales your memory can contain. Even the largest things a human normally contemplates, countries, continents, the ocean, are tiny compared to the solar system. And the solar system is tiny compared to the galaxy. And the galaxy is one of hundreds of billions of galaxies in the observable universe. At some point, in thinking about these scales, the numbers stop working as numbers and start working as concepts of the incomprehensible. 225 million years for one galactic orbit. 448,000 miles per hour of orbital speed. 20 galactic laps since the solar system formed. These are not numbers that mean anything in ordinary life. They don't map onto anything. Human experience is equipped to feel. But here is the thing that does mean something. You are part of it. Not as a passenger. Not as an observer looking at it from outside. As a constituent element. The atoms of your body have been part of this galactic journey for billions of years. Long before there was a solar system, the atoms that would eventually become part of you were drifting through the galaxy as gas, as dust, as parts of molecular clouds. Some were forged in the core of a star that exploded billions of years ago, scattering them into the interstellar medium. Some were present since the Big Bang, hydrogen atoms that have been part of various structures across cosmic history. All of them were already moving through the Milky Way in some state, in some form, long before the solar system formed. When the solar nebula collapsed and the sun ignited and the planets formed, those atoms were caught up in the new system. They've been riding the solar system's orbit ever since. They will continue riding it long after every arrangement we call a person or a civilization or a species has dissolved back into simpler forms. The journey doesn't begin at birth. The journey is as old as the atoms, and it doesn't end when you do. The atoms continue. They will end up somewhere, perhaps in the oceans of another planet, perhaps in the interior of a star, perhaps drifting alone through the galactic halo for billions of years. But they will continue the journey. The corkscrew through the galaxy will keep turning. The constellations you know will not last. This is a fact that rarely surfaces in conversation, but is true and verifiable. The patterns visible in Earth's sky are not permanent arrangements of stars. They are temporary configurations produced by the current positions of stars that happen to appear close together from Earth's current location in space. The stars in a constellation are not actually near each other. Orion, for example, is an arrangement of stars at vastly different distances. Rigel, Orion's bright blue foot, is about 860 light-years away. Betelgeuse, the famous red shoulder, is roughly 650 light-years away. Mintaka, one of the belt stars, is about 900 light-years away. These stars are nowhere near each other in three-dimensional space. They only appear to form a pattern because of where Earth happens to be sitting in the galaxy. And as Earth moves with the solar system, and as those stars move on their own orbits, the pattern changes. 100,000 years ago, the constellations looked different. The stars were in different positions relative to each other and to us. 100,000 years from now, they will look different again. The Big Dipper will not always look like a dipper. Orion will not always look like a hunter. The Southern Cross will not maintain its current shape. Everything is moving. The patterns are momentary. They dissolve on the same timescales as the galactic motion that produces them. The ancient cultures that named those constellations gave them permanence in myth. The physics gives them only temporary existence in the sky. The sky you see tonight will not exist in the same form 100,000 years from now. The stars will still be there. But the patterns will have drifted into new arrangements that no one in this era has named. There is one more thread worth following. The nature of our motion through the galaxy and the history of how we came to understand it says something about how knowledge works. For most of human history, the sky appeared still. The stars appeared fixed. The galaxy appeared, to the extent it was noticed at all, as a static feature of the heavens. And the conclusion that followed, that we were stationary, or at the center of things, or otherwise specially placed, was not stupid. It was a reasonable inference from the available evidence. The available evidence was just radically incomplete. Every significant expansion of our picture of how the solar system moves came from new tools. The telescope showed the Milky Way was stars. The spectroscope showed stars had velocities. Radio telescopes showed the galactic structure through the dust. Space-based infrared observatories showed the galactic bar and the central regions. The Gaia satellite showed the disk was disturbed and rippling. Each new tool revealed a layer of motion that was invisible before. Each revelation required revising conclusions that had seemed secure. And each revision made the reality richer, more complex, and more interesting than the model it replaced. There is no reason to think this process is finished. The Gaia data is still being analyzed. Future space missions will measure stellar positions with even greater precision. Gravitational wave observatories will eventually detect the background of gravitational waves from merging supermassive black holes, providing a new way to probe galactic and intergalactic dynamics. The picture will keep changing. What we know now is far more accurate than what was known 50 years ago. It will be far less accurate than what is known 50 years from now. That's not a failure of current knowledge. That's how knowledge works. Each generation builds the best picture it can from the tools available and hands a better picture to the next generation. We are inside that process right now. The solar system is moving through the galaxy. We know that much with certainty. The exact shape of its path, the precise history of its galactic environment, the detailed structure of the dark matter, halo, it moves through. These are known with increasing but imperfect precision. The questions that remain are not gaps to be embarrassed about. They are the frontier, the edge where the next generation of instruments and observations will push the picture forward. The galaxy has a heartbeat, not literally, but there is a rhythm to some of what happens in the Milky Way that astronomers have been trying to understand for decades. The gamma-ray Fermi bubbles are part of it. Those enormous lobes of emission rising tens of thousands of light-years above and below the galactic plane, discovered by the Fermi Space Telescope in 2010, show that the galactic center has had episodes of dramatic activity. The current Sagittarius A is quiet by the standards of active galactic nuclei. Compared to quasars in the distant universe, galaxies with supermassive black holes actively devouring enormous quantities of gas and shining with the energy output of trillions of suns. Sagittarius A is barely whispering, but it has not always been this quiet. The Fermi bubbles are thought to have formed a few million years ago. A massive burst of energy from the galactic center, most likely a large accretion event where Sagittarius A consumed a significant quantity of gas in a relatively short time, blew hot material out of the galactic plane. That material rose, cooled, and remained as the structures we see today. The energy involved in creating those bubbles was extraordinary. The equivalent of millions of supernova explosions, all occurring in a geologically brief interval. And the solar system was already near its current position when this happened. The event was 26,000 light-years away. At that distance, the effects on the solar system were probably minimal. The energy dispersed over an enormous volume of space before reaching us. But the galactic center's history of periodic outbursts means the solar system has experienced varying galactic center activity over its lifetime. When the solar system was younger and the galaxy was more actively accreting, those outbursts were more frequent and more energetic. The galactic environment of the early solar system was noisier than today's. And as the solar system moves on its orbit, it moves through the echoes and remnants of those past events. Cosmic ray distributions, shaped by past outbursts, gas and dust structures, disturbed by ancient galactic center activity. The galaxy's history is part of the solar system's environment. There is no clean separation between galactic history and solar system history. They are interwoven. The Milky Way is consuming smaller galaxies right now. This is not a rare or unusual event. It is normal galactic evolution. Large galaxies grow by absorbing smaller ones. The Milky Way has done this many times over its history, and it is doing it today. The Sagittarius dwarf galaxy has been in the process of being absorbed for billions of years. Each orbit brings it closer to complete disruption. Its stars, stripped from their original galaxy by the Milky Way's tidal forces, are spread into long streams that wrap around the Milky Way multiple times. If you know where to look and have the right instruments, you can see these streams. They were first detected in the late 1990s, when astronomers studying the distribution of stars at the outer edges of the Milky Way noticed coherent structures, ribbons of stars, all moving in the same direction that didn't fit the expected smooth distribution of the galactic halo. Those ribbons were the Sagittarius stream, the dispersed remnants of a galaxy being consumed. The large and small Magellanic Clouds are also being disrupted. These two irregular satellite galaxies, visible from the southern hemisphere as hazy patches of light, orbit the Milky Way on a complex path. They, too, are being stripped of their outer stars by tidal forces. The Magellanic Stream, a ribbon of hydrogen gas stretching across about 200 degrees of the sky, is the material being pulled out of the Magellanic Clouds by the Milky Way's gravity. Eventually, in billions of years, the Magellanic Clouds will be fully incorporated into the Milky Way. Their stars will become part of the galactic halo, and perhaps their gas will trigger new rounds of star formation in the disk. The Milky Way is not a static structure. It grows. It consumes. It changes. And the solar system moves through a galaxy that has been in this process of growth and disruption throughout its entire history. Stars from the Sagittarius dwarf and from earlier mergers, now unidentifiable, are scattered through the galactic halo and even the thick disk. Some of those stars are close enough to the solar system to have their velocities measured by Gaia. They are recognizable by their chemistry, lower concentrations of heavy elements than disk stars, reflecting their origin in a smaller galaxy with a different enrichment history. They are visitors in the disk, travelers from galaxies that no longer exist as distinct entities. The sun's light takes a specific amount of time to reach each planet. Light from the Sun reaches Mercury in about 3 minutes, Earth in about 8 minutes, Jupiter in about 43 minutes, Neptune in about 4 hours, and the heliopause, the boundary of the heliosphere, where the solar system's direct influence on the interstellar medium, ends in about a day and a half at the speed of light. The Oort cloud, at its outer reaches, is so distant that light takes about a year and a half to reach it. It is simultaneously part of the solar system and on the edge of interstellar space. Objects there are on the boundary. They are weakly bound to the Sun. They are susceptible to the galactic tide. They are susceptible to perturbations from passing stars. They are, in a real sense, the frontier of the solar system's gravitational domain. Beyond the Oort cloud, the interstellar medium takes over. The medium that the solar system is moving through. The thin sea of gas and dust and cosmic rays and magnetic fields that fills the space between the stars. And the solar system plows through it all, its heliosphere pressing against it on the leading edge, pushing material aside, dragging it along at the sides, creating a long heliotail behind it. The heliosphere is the solar system's wake, the signature of our passage through the interstellar medium. When astronomers build better instruments to study the interstellar medium in detail, they will be able to detect that wake. A region of disturbed interstellar gas and dust trailing behind the solar system's direction of travel. A fossil of our motion, written in the medium we're moving through. Something worth understanding about the galactic orbit is that it is not precisely circular. No orbit in a complex gravitational environment is perfectly circular. The Sun's orbit around the galactic center is slightly elliptical. Over the course of each galactic year, the Sun moves slightly closer to the galactic center and then slightly farther away. The variation is modest, perhaps a few thousand light-years over the course of an orbit, but it's real. This means the Sun periodically moves into a somewhat denser stellar environment when it's at its closest approach to the galactic center, and into a somewhat sparser environment when it's at its greatest distance. The star density near the galactic center is far higher than in the Sun's current neighborhood. Stars in the inner galaxy are packed much more tightly. The rate of stellar encounters is higher. The radiation environment from nearby massive stars is more intense. The galactic center region, with its supermassive black hole and dense stellar clusters, is a dramatically different environment from the quiet suburb the Sun currently occupies. The Sun never gets close enough to the galactic center to experience those extreme conditions directly. Its orbit keeps it in the middle distance region of the disk, where conditions are relatively benign. But the ellipticity of the orbit means it's not always at exactly the same galactic radius. The environment varies slightly over each galactic year. This is another layer of the solar system's dynamic relationship with the galaxy. Not just the sweeping orbit and the vertical oscillation. Also, the slow, gentle oscillation in galactic radius as the slightly elliptical orbit brings the Sun closer to and farther from the galactic center over each 225 million year cycle. The discovery of exoplanets, planets orbiting other stars, has added a new dimension to understanding the solar system's place in the galaxy. Since the first confirmed detection of an exoplanet around a Sun-like star in 1995, astronomers have catalogued thousands of planetary systems. What they've found is that planets are common, extraordinarily common. Most stars appear to have planets. The galaxy contains vastly more planets than stars. But the solar system's architecture, with small rocky planets in the inner system and gas giants in the outer system, arranged in nearly circular orbits with wide spacing, is not the most common arrangement seen in the exoplanet catalogue. Many exoplanet systems have large planets in very close orbits around their stars. Systems where a giant planet, sometimes larger than Jupiter, orbits closer to its star than Mercury orbits the Sun. These are called hot Jupiters, and their formation is thought to involve migration, the planet forming farther out, and then spiraling inward through gravitational interactions with the disk of gas and dust from which the system formed. In a system with a hot Jupiter, the inner rocky planets, if any existed, would have been destroyed or thrown out during the giant planet's migration. The solar system does not have a hot Jupiter. Jupiter is at 5 astronomical units from the Sun, far enough out that the inner rocky planets formed and survived. Whether this makes the solar system unusual or just one end of a distribution is still debated. The exoplanet catalogue has selection biases. Certain types of planets and orbits are easier to detect than others, so the true distribution of solar system architectures is still being worked out. But the solar system's specific arrangement, which led to the development of Earth as a habitable rocky planet, may be less common than once assumed. And if planetary architecture affects the odds of complex life developing, then the galactic distribution of different architectural types matters. The solar system is moving through a galaxy where most stars have planets, but many of those planetary systems look quite different from ours. The specific path the solar system has taken through the galaxy, the specific position it has occupied in the galactic disk, may have contributed to its specific history in ways that connect the largest scales of galactic structure to the smallest scales of a living planet. Let me say something about how we actually measure the motion we've been discussing. Because there's a tendency, when talking about astronomical measurements, to treat the numbers as if they simply appeared, as if astronomers looked up and the velocities were just there. They weren't. Every number mentioned in this account is the result of decades or centuries of careful, difficult observation and interpretation. Measuring how fast the Sun is orbiting the galactic center requires knowing two things: the Sun's orbital speed and its distance from the galactic center. Neither is directly observable. The distance to the galactic center cannot be measured directly because interstellar dust blocks the view. Astronomers have to use indirect methods, measuring the distances to objects whose distance can be inferred from their properties, such as pulsating variable stars or massive star clusters near the galactic center, and using those as distance markers. Different methods have historically given somewhat different answers. The current best estimate of about 26,000 light-years is the result of combining multiple independent methods and checking them for consistency. Measuring the orbital speed requires measuring how fast nearby stars are moving relative to us, and using the pattern of those motions to infer the bulk orbital velocity. If you're on a merry-go-round and you want to know how fast it's spinning, you look at how the landscape moves relative to you. Astronomers do the same thing with stars. The pattern of stellar velocities in different directions, some approaching, some receding, in characteristic patterns determined by differential galactic rotation, allows the orbital speed to be calculated. Again, different methods have historically given somewhat different answers. The vertical oscillation period, 60 to 90 million years, comes from measuring the gravitational potential of the galactic disk, the density of mass in the disk, and calculating how strongly that mass pulls objects back toward the midplane when they stray above or below it. The estimate depends on knowing how much of the disk mass is invisible stars and gas versus dark matter, and the dark matter component introduces significant uncertainty. 60 to 90 million years is a range, not a precise number. Future measurements may narrow it. But the oscillation itself is not in doubt. The physics demands it. Every number in this account carries uncertainties. Every measurement is an approximation, subject to revision as new data arrives. That is not a weakness. It is the nature of science at the frontier. And the frontier here is genuinely productive. The Gaia satellite is improving the measurement precision of nearby stellar velocities by orders of magnitude. That data will allow much more precise determination of the galactic potential, the three-dimensional gravitational landscape through which the solar system moves. And from the galactic potential, more precise determination of the orbital parameters. The numbers will sharpen. The picture will become clearer. The fundamental story, helix, corkscrew, dark matter halo, Andromeda approaching, will remain. But the details will improve. And in the details lies the full richness of the solar system's journey through the galaxy. The chemical fingerprint of the solar system tells us something about the galactic neighborhood where it formed. Stars form in molecular clouds, vast, cold, dense regions of gas where the temperature is just a few degrees above absolute zero, and the density is high enough for gravity to pull material together into new stellar systems. The Sun's molecular cloud has been gone for 4.5 billion years, dispersed by the energy of the stars it formed, including the Sun itself, long ago. But the chemistry of the solar system carries a record of that cloud's composition. The proportions of different elements in the Sun, what spectroscopists call its metallicity, meaning the abundance of elements heavier than hydrogen and helium, reflect the history of nucleosynthesis in the region of the galaxy where the Sun formed. The Sun's metallicity is broadly typical for a star of its age formed in the galactic disk. Not unusually rich in heavy elements. Not unusually poor. Average, by the standards of disk stars, formed around the same time. This is consistent with the Sun forming somewhere in the middle disk, in a region with a typical enrichment history, rather than in the metal-poor outer disk or the metal-rich inner disk near the galactic center. Some researchers have used the Sun's chemical composition to try to constrain where in the galaxy it formed. Because stars at different galactic radii have different average metallicities, a result of the inside-out formation of the galaxy, where the inner regions were enriched more rapidly by early star formation. The Sun's metallicity is mildly consistent with having formed somewhat closer to the galactic center than it is today. Perhaps at a galactic radius of around 23 to 24,000 light-years, rather than the 26,000 light-years it now occupies. If this is correct, the Sun has migrated outwards slightly over its lifetime. Galactic radial migration, the process by which stars slowly change their average galactic radius through gravitational interactions with the disk, is now recognized as a significant phenomenon. Stars can be scattered to larger or smaller galactic radii by interactions with spiral arms and the galactic bar. The Sun may have drifted outward from a slightly more inner birth location over 4.5 billion years. If so, it has been a slow journey, adding to the already complex picture of how the solar system moves through the galaxy. Not just the vertical oscillation and the orbital sweep, but also a very gradual, very slow drift in average galactic radius. A migration that happens so slowly it's invisible over any human timescale, but significant over billions of years. Here is the scale of the solar system's journey in a different dimension. In the 4.5 billion years since the solar system formed, how far has it actually traveled? The orbital speed of around 500,000 miles per hour, sustained for 4.5 billion years. 4.5 billion years is about 39 trillion hours. Multiply 39 trillion hours by around 500,000 miles per hour. The result is roughly 17.5 quadrillion miles. 17.5 followed by 15 zeros. That is the approximate total distance the solar system has traveled through the galaxy since its formation. It is a meaningless number in the sense that no human intuition can relate to it. But it is real. Every mile of it required energy, the gravitational dynamics of the galaxy, maintaining the orbit against perturbations, the angular momentum inherited from the galaxy's formation, preserved through all those billions of years. And the journey is not finished. The Sun has roughly 5 billion years of main sequence life remaining before it begins to swell into a red giant. 5 billion more years at around 500,000 miles per hour. Another 20 galactic orbits to go. Another 20 corkscrew laps through the galactic disk. Another enormous stretch of interstellar space to traverse, through environments that don't exist yet, past stars that haven't formed yet, in configurations no current mind can predict. The journey the solar system has taken so far is roughly half over. The second half is still being written. There is something strange about the way we talk about space that deserves attention before we go further into what the solar system's motion means. We use the word empty a lot. Space is empty. The interstellar medium is almost empty. The voids between galaxies are essentially empty. And this is technically true if you compare the density of interstellar space to the density of, say, water, or even the best vacuum achievable in a laboratory on Earth. The interstellar medium, the gas and dust that fills the space between stars in the Milky Way's disk, has a density of roughly 1 atom per cubic centimeter in the denser regions. 1 atom per cubic centimeter. The best vacuum achievable in a laboratory contains perhaps a few hundred molecules per cubic centimeter. Interstellar space is more empty than anything we can create in a lab. But here is the thing about that almost empty space. The galaxy is enormous. And when you multiply a tiny density by an enormous volume, you get enormous mass. The diffuse interstellar medium, all that thin gas spread across the disk, contains enough material to build millions of new stars. It's not just the raw hydrogen and helium inherited from the Big Bang, either. The interstellar medium contains complex molecules. Astronomers have detected more than 200 distinct molecular species in interstellar space: water, ammonia, formaldehyde, ethanol, glycine, and amino acid, even simple sugars. These molecules exist in dense molecular clouds, regions where the gas is thick enough to shield the interior from the ultraviolet radiation that would otherwise destroy complex chemistry. The solar system has passed through regions of the interstellar medium with varying densities and compositions over its 4.5 billion year journey. Some of those passages may have left traces. Interstellar dust grains can carry organic molecules. Comets, formed from the cold outer regions of the solar nebula, contain complex organic chemistry. The question of whether the interstellar medium has contributed organic material to Earth over its history, material that could have had relevance to the origin of life, is an active area of research. The solar system has not been sealed off from its environment. It has been moving through a sea of gas and dust and radiation for its entire existence. Some of what's in that sea has made it to Earth. Some of it may matter. The interstellar medium through which the solar system moves is not uniform, even on small scales. Our local region of the galaxy is particularly interesting. The Sun currently sits inside a structure called the local bubble. The local bubble is a cavity in the interstellar medium, a region roughly 1,000 light-years across, where the density of gas is much lower than average. The bubble is surrounded by a shell of denser gas and dust. Inside, the medium is thin and hot, much hotter than the average interstellar medium, and much less dense. What created this bubble? Supernova. Roughly 10 to 20 million years ago, a series of supernova explosions in the region carved out this cavity. The blast waves from those supernovae drove the surrounding gas outward, creating the shell that now surrounds the local bubble. The hot gas left inside is still slowly cooling and expanding. The Sun entered this bubble about 5 million years ago, based on estimates of when the bubble formed and the Sun's motion through the local interstellar medium. Before that, the Sun was moving through denser regions of the disk. The local bubble affects the interstellar environment of the solar system. The galactic cosmic ray flux the background of high-energy particles reaching the solar system from across the galaxy is modified by the structure of the interstellar medium between the source and us. A denser medium provides more shielding. A thinner medium like the local bubble provides less. The exact effects are subtle and complex, and they're still being worked out. But the solar system has been in a thin medium environment for the last several million years. It was in a different environment before that, and it will be in a different environment again as it continues its galactic journey. The interstellar medium the solar system is moving through is not a static backdrop. It's a changing environment with history and structure. The solar wind, the constant stream of charged particles flowing outward from the Sun in all directions, creates a bubble of its own around the solar system. This bubble is called the heliosphere. It extends out into space in all directions, carving a cavity in the interstellar medium around the solar system. The boundary where the solar wind meets the interstellar medium is called the heliopause. The Voyager probes, launched in 1977, crossed the heliopause. Voyager 1 crossed it in 2012. Voyager 2 followed in 2018. After the heliopause, the probes entered true interstellar space, the medium between the stars. The data they sent back from the heliopause and beyond has been invaluable. It showed that the boundary between the solar system and interstellar space is real and sharp. The density, temperature, and composition of the medium changed distinctly. Outside the heliopause, Voyager detected the interstellar medium directly for the first time. The heliosphere is not spherical. It's elongated in the direction of the solar system's motion through the interstellar medium. The leading edge, the nose of the heliosphere, pointing in the direction the solar system is moving, is compressed by the ram pressure of the interstellar medium flowing past. The trailing edge, the tail is stretched out into a long structure, sometimes called the heliotail. The heliosphere is shaped by its motion through the interstellar medium, the same way the bow of a ship is shaped by its motion through water. And as the density and composition of the interstellar medium changes as the solar system moves through different regions of the galaxy, the heliosphere changes too. In denser, interstellar environments, the heliosphere is compressed, offering less protection to the inner solar system. In thinner environments, like the local bubble, the heliosphere expands. The galactic environment shapes the heliosphere. The heliosphere shapes the radiation environment of Earth. The connections are indirect and subtle, but they're real. Let's spend a moment on the specific stars that make up our local neighborhood, because they reveal something about the solar system's galactic setting. The nearest stars to the Sun are the Alpha Centauri system, 3 stars at just over 4 light-years. Then Barnard's star, a red dwarf, at about 6 light-years. Then Wolf, 359, another red dwarf, at about 8 light-years. Then Lalande, 21185, at about 8.5 light-years. Then, the binary system, Sirius A and B, at about 8.5 light-years. The pattern is clear. Most of the nearest stars are red dwarfs. Red dwarfs, stars with masses less than about 40% of the Sun's, are the most common type of star in the galaxy. They are dim, cool, and extraordinarily long-lived. A red dwarf, with half the Sun's mass, will shine for roughly 80 billion years. That's about 6 times the current age of the universe. Red dwarfs are so frugal with their fuel that many of them will still be burning long after the Sun has swollen into a red giant, ejected its outer layers, and cooled into a white dwarf. In the solar neighborhood, within about 30 light-years of the Sun, there are estimated to be several hundred stars. The vast majority are red dwarfs. Sun-like stars, yellow dwarfs of the G and K spectral types, are a small minority. And massive, hot, blue stars are almost entirely absent from the local neighborhood. That's expected. Massive stars are rare to begin with. The galaxy produces far fewer of them than it does red dwarfs. And they don't live long enough to drift far from the spiral arm regions where they form. The local neighborhood, being between the major arms, is relatively free of the young, massive stars that characterize the arms themselves. The nearest star that is significantly more massive than the Sun within about 100 light-years is Sirius A, about twice the Sun's mass, still a relatively modest object. The nearest truly massive star is much farther away. The Sun's neighborhood, in short, is a quiet suburb. Middle-aged stars of moderate mass. Low-key, stellar activity. No nearby supernovae in the immediate vicinity for millions of years, based on the absence of young massive stars close by. Quiet, by galactic standards. And the solar system has been sitting in this kind of neighborhood, broadly speaking, for its entire history. Whether that quiet neighborhood is part of what allowed a complex biosphere to develop on Earth is one of the interesting open questions in astrobiology. The Sun's neighborhood will not stay the same. As the solar system moves through the galaxy, the local stellar neighborhood changes. Stars drift relative to each other. Close passes, not within colliding distance, but within a light-year or two, do occur over geological timescales. A star passing within a light-year or two of the solar system would perturb the Oort cloud gravitationally. The closer the pass, the stronger the perturbation. Close stellar encounters are rare but not unknown. Astronomers have identified several stars that will pass relatively close to the solar system in the next few million years. Gliese 710, a red dwarf, is currently about 62 light-years away, but is approaching. In about 1.3 million years, it will pass within roughly 0.1 of 7 light-years of the Sun, about 10,500 astronomical units. That puts it well inside the Oort cloud, close enough to send significant gravitational disturbances through it, and potentially trigger comet showers into the inner solar system for millions of years afterward. It will not come anywhere near the planetary orbits, but its effect on the outer solar system will be substantial. Earlier in the solar system's history, even closer passes have occurred. The geological record of comet impacts on Earth and the other planets carries, encoded in it, some history of such encounters. The Oort cloud remembers these passages. Each close stellar encounter leaves a gravitational signature, a pulse of cometary activity, as disturbed Oort cloud objects are redirected inward. Some of those objects strike. Most don't, but some do. The history of impacts in the solar system is, in part, a history of the solar system's journey through the galaxy and the gravitational encounters that journey has brought. We have established the basic picture of the solar system's motion through the galaxy. Now, let's look at what that motion means on the most immediate human timescale, what we can actually observe and measure. Every year, astronomers measure the velocities of nearby stars with increasing precision. What they find is that the local stellar neighborhood is not a uniform, smoothly orbiting community. It's a mix of stellar populations with different ages, different compositions, and different velocity signatures. Old stars, those formed early in the galaxy's history, tend to have higher random velocities relative to the galactic orbit. They've had billions of years of gravitational interactions to randomize their orbits somewhat. Young stars recently formed from molecular clouds in the spiral arms tend to have lower random velocities. They've recently inherited the orderly rotation of their parent gas cloud and haven't had time to be perturbed. The Sun falls somewhere in the middle. At 4.5 billion years old, it's neither a young thin disk star nor an ancient thick disk star. Its velocity relative to the local standard of rest that 12 miles per second drift toward Hercules is typical for a middle-aged disk star. This tells us something about the Sun's history. It was almost certainly born in a spiral arm, as part of a cluster of stars that formed from the same molecular cloud. Over billions of years, that cluster has dispersed. Its members have drifted apart as their individual orbits diverge slightly. The siblings of the Sun stars, born from the same cloud at roughly the same time, with initially similar compositions, are now scattered across the galaxy. Some are closer to the galactic center. Some are farther out. Some have drifted into different galactic latitudes. The Sun's birth cluster no longer exists as a recognizable structure, but astronomers have been searching for the solar siblings. If stars form from the same cloud, they should have similar chemical compositions, similar ratios of heavy elements that are the fingerprints of the specific supernova history of their parent cloud. By measuring stellar compositions with high-resolution spectroscopy and comparing them to the Sun's, astronomers can identify stars that are chemically compatible with being solar siblings. A few hundred candidates have been identified. Some are relatively nearby. None are confirmed definitively as birth siblings. But the search continues. The Sun was not born alone. It had thousands of birth siblings. They are out there, somewhere in the galaxy, still moving on orbits shaped by the same initial conditions that shaped the Sun's orbit, drifting away. Part of the same story. Here is something that tends to get lost in discussions of galactic motion. The solar system's journey through the galaxy has changed the solar system itself. Not dramatically, not on any scale visible in a human lifetime. But over billions of years, the galactic environment has left its mark. The composition of the interstellar medium that forms the context for the solar system is not uniform through time. The galaxy has been producing heavy elements, elements heavier than hydrogen and helium, since its first generation of massive stars formed and exploded roughly 13 billion years ago. Each supernova seeds the interstellar medium with heavy elements. Each generation of stars forms from slightly more enriched material than the last. The Sun formed 4.5 billion years ago from material that was already moderately enriched. It has higher concentrations of heavy elements than ancient stars formed early in the galaxies. History. Earth is made of those heavy elements. Your body is made of them. Iron, calcium, carbon, nitrogen, oxygen. All of it was in the galactic medium before the solar system formed. All of it was processed through earlier stellar generations. All of it was distributed across the galaxy by stellar winds and supernova explosions. The solar system incorporated it when it formed. And the galactic environment the solar system has moved through since formation has continued to deliver material to it, however slowly. Interstellar dust grains enter the solar system. Cosmic rays carry interstellar atoms. The heliosphere is not a perfect barrier. The solar system is embedded in the galaxy, and the galaxy's chemistry reaches in. We are not an isolated island in the Milky Way. We are part of it, participating in its chemical evolution in the most literal sense. In the 1990s, astronomers made a discovery that permanently changed our understanding of the solar system's place in a larger context. The Hipparcos satellite, the predecessor to Gaia, measured the positions and proper motions of about 120,000 stars with unprecedented precision. From those measurements, astronomers could identify stellar streams, groups of stars, moving through the solar neighborhood with similar velocities. Not just similar, suspiciously similar. Far more similar than you'd expect from random chance. These stars were moving together in coherent groups, like schools of fish in a slow-motion, stellar ocean. Some of these streams are the remnants of star clusters that formed together and have since dispersed. Stars born together tend to have similar velocities because they formed from a common cloud with a common initial velocity. Over time, the cluster spreads out as slight orbital differences cause the members to drift apart. But the velocity similarity persists long after the cluster has dissolved. The velocity is a fossil, a memory of the birth conditions preserved in the orbital dynamics. Other streams are more complex. They're the result of resonances with the galactic bar or spiral arms, collecting stars into organized velocity groups through gravitational dynamics rather than common birth. What this means for the solar system is that we are not a lone traveler through the galaxy. We are moving in a galactic current. The solar neighborhood contains stars at various stages of various streams, all moving in broadly organized patterns through the disk. The Sun is part of this organization. Its velocity relative to the local standard of rest, that modest 12 miles per second drift toward Hercules, places it within a specific region of the local velocity field. We are not exceptional. We are participants in a larger flow, moving through the galaxy not as an isolated family of planets around a star, but as part of a loose community of stars, all drifting together through the galactic disk, shaped by the same forces, responding to the same gravitational tides. There is a measurement that brings all of this down to something almost tangible. Every year, astronomers release updated catalogues of the radial velocities of nearby stars. These measurements show stars moving toward us and away from us at tens of miles per second. Some of those stars are approaching. Some are receding. Some will eventually come closer than any star is today. Some are fading into the distance, never to return. If you take the full three-dimensional velocity of Proxima Centauri, our current nearest stellar neighbor, and project it forward in time, the curve is unambiguous. Proxima is currently moving toward us. In about 27,000 years, it will be as close as it ever gets, roughly 3.1 light-years. Then it begins moving away. In about 33,000 years from now, it will be farther than it is today. In a few 100,000 years, it will be far enough that a different star will take the title of nearest neighbor. These changes happen too slowly for any individual human to notice. But they're real. The night sky is a dynamic system. The stellar neighborhood is always in flux. Stars approaching, stars receding, the galactic current carrying everything forward in time through configurations that have never existed before and will never exist again. The specific arrangement of stars in the sky tonight is unique. It exists for this one brief moment in galactic history. In 100,000 years it will be gone, dissolved by the slow drift of stellar velocities into a new arrangement that no human has ever seen. Let's bring the picture all the way back to where we started. You, standing still, not feeling any motion. The sun above, the stars frozen in their patterns, the ground solid beneath your feet. The impression of stillness is so complete and so persistent that it requires genuine effort to override it. But the override is worth the effort. Because the reality of your situation is far more extraordinary than the impression. Right now, in this moment, you are sitting on a planet orbiting the sun at 67,000 miles per hour, orbiting with the entire solar system around the galactic center at around 500,000 miles per hour, oscillating slowly through the galactic plane on a cycle of 60 to 90 million years, drifting 12 miles per second toward the constellation Hercules relative to the local stellar neighborhood, moving with the entire Milky Way toward the Great Attractor at 1.4 million miles per hour, falling with the Great Attractor toward the Shapley supercluster, and expanding away from distant galaxy clusters as the universe stretches. All of this simultaneously, right now. None of those motions is noticeable in daily life. None of them produce any sensation you can detect without instruments. The brain is not built to perceive them, but the instruments show they're there. The mathematics confirms them. The physics demands them. And understanding them changes something, however slightly, about what it means to exist in this universe. Not the immediate practical facts of your life. Those stay the same. But the context, the frame, the knowledge of where you actually are and how you're actually moving. That knowledge is available now in a way it wasn't available to any human who ever lived before the last 2 centuries. We are the first generations of humans to know the true shape of the journey. The first to know we're inside a galaxy, not at the center of the universe. The first to know the galaxy is one of hundreds of billions. The first to know the solar system moves through the galaxy on a corkscrew path, rather than a flat circle. The first to know the disk is warped and rippled and disturbed. The first to detect the dark matter halo through its gravitational effects on our orbit. The first to know Andromeda is coming. All of that knowledge was earned by centuries of patient observation and mathematical reasoning. It was earned against resistance, against earlier comfortable assumptions, against the human preference for simplicity and special positioning. It is extraordinary that we have it, and it is ours to use. Not just to understand the universe better, but to understand our place in it more honestly and more completely. We are on a corkscrew through the Milky Way. We are inside a dark matter halo. We are passengers in a galaxy falling toward a supercluster. We are part of an ongoing cosmic story that began 13.5 billion years ago and will continue long past any timescale we can project. And right now, tonight, the journey continues. The next time you stand outside on a clear night and look at the Milky Way, that band of faint, unsteady light stretching from horizon to horizon, understand what you are looking at. You are inside it. The light reaching your eyes from that band has traveled from stars hundreds to tens of thousands of light years away, all of them in the galactic disk, all of them moving on their own orbital paths. The dark patches in the band are dust clouds, silhouetted against the background glow of billions of stars. The denser, brighter region toward the constellation Sagittarius is the direction of the galactic center, hidden behind layers of dust, but pulling the entire disk in its orbit. Every point of light you see is a journey. Every star is a traveler. None of them are still, and you are among them. The solar system is on a corkscrew path through this disk, sweeping around the galactic center at around 500,000 miles per hour, while oscillating through the plane. At this moment, right now, you are 80 light-years above the galactic midplane, moving toward it, moving toward Hercules, moving with the entire local group toward the great attractor, moving within a galaxy, approaching another galaxy, 2.5 million light-years away, moving as part of a universe that has been in motion since the first fraction of a second after its beginning. None of this is metaphor. Every statement is a measurement. Every number is the result of decades of painstaking observation and calculation. This is what the universe actually is. This is where you actually are. Not still. Not at the center. Not on a flat circle. On a helix, through a disk, in a galaxy, in a universe, all of it in motion. All of it right now. And the motion will continue long after anything on this planet is here to know about it. The corkscrew keeps turning. Good night.